Hey everyone, in this video we're going to look at the next type of transformation. So we're looking at reflections here. So in the following diagram you have triangle ABC. It's been reflected over the line M to produce triangle A prime, B prime, C prime as shown. The other important thing here is our diagram is drawn to scale. So remember, a reflection always needs a line to reflect over. We dealt with rotations in the previous lesson, and we saw that there was a center that we rotated around because it kind of goes in a circular pattern. So really with a rotation, you just need some point to rotate around. For a reflection, you need a line to reflect over because every part needs to be mapped over. So we're going to draw in the segments A to A prime, B to B prime, and C to C prime here. And it can just be as best as you can. It doesn't have to be perfect. But the angle that's formed now between the line of reflection and the original point with the image point is 90 degrees, right? So we're making right angles there. So we know that our line of reflection should always be perpendicular to the segments that are in between. So like that original and pre-image, or that pre-image and image point. Now we're going to mark the intersections of A to A prime, B to B prime, and C to C prime, okay? These points are all the midpoints relative to each individual segment, okay? They're going to bisect our segment. So each segment's bisected through that point. So if we have the line of reflection here, notice it's making right angles with our pre-image and image. It's also cutting that distance in half. It's like falling right in between. The line of reflection is always a perpendicular bisector. We're going to see that in a couple more examples as we keep moving forward. So if I go down to exercise number 2, now I'm dealing with a isosceles triangle ABC. Now, it's been a while since we talked about isosceles, but remember they have 2 congruent sides. So in this case, they tell me that my congruent sides are AB and AC, and I'm marking them as shown, just so you have their little marks given. The vertex angle of BAC is where it's been bisected by the ray AD. Now, the non-vertex angles, there's always 2 of them in here in this case. Those are known as the base angles. They're located across from the sides that are equal. So what I mean by that is AB is across from C. There's one of my base angles. AC is across from B. There's my opposite base angle. And what we should know is that an isosceles triangle not only has 2 congruent sides, but they have 2 congruent base angles. So angle B is congruent to angle C. Okay, that's true for every isosceles triangle, not just ones that have a bisector running through their vertex angle. Now, notice in this case, if we have a congruent angle over here, because that's been bisected, so those 2 are going to be equal. We have the congruent angles B and C, and we also have AB congruent to AC. We're having a lot of parts that are like lining up to one another. BD is also equidistant to DC. So what's true about these 2 segments? They are congruent. Let me make that symbol a little bit better. Right? So they are congruent to one another. They're both equidistant from D. So both those points B and C are equidistant from D. If we reflected triangle ADC across the ray AD, explain why the points A and D do not change their location. So I'm going to take away some of my markings right now, but I'm thinking about if I wanted to reflect ADC. Now ADC is this triangle on the right side. Notice if we wanted to reflect over AD, well, in this case, A and D are already on that line of reflection. So if we think back to what we were just talking about, if the line of reflection is a perpendicular bisector of the points, well, these points are already on the line of reflection, so they're not going to move anywhere. So A and D do not change their location. because they lie on the line of reflection. And we kind of saw that when we were talking about rotations. The center of rotation, when we're turning around it, if that's part of your line, it's not going anywhere, right? The center of rotation is being used, so it's not going anywhere. The other point will move. But if you have 2 points on the line of reflection, then these ones are just staying exactly on that line of reflection. So we already know that AD is not going anywhere. If triangle ADC was reflected across AD, explain why the point C must fall on B. Well, we said it before, because B, D, and DC are congruent. Both B and C are equidistant to D. So both of those points are equidistant from D. D is that midpoint because if we're thinking about what we said before, that's our line of reflection. We had all those angles that matched up to one another, but since AD is the line of reflection, D is the midpoint of BC, and a line of reflection is also known as a perpendicular bisector. So remember that upside down T, that's there for perpendicular, which means it forms congruent right angles. Bisector means it cuts a segment in half. And if I go in and look here, when we want to talk about those two angles that are given, ADB and ADC are going to have to be congruent right angles because we said the line of reflection not only passes through the midpoint, D, but it also is perpendicular, so it has congruent right angles. So the big thing to take away from this so far is that any line of reflection is a perpendicular bisector from the segments, or like from the original image to the to the new image. Now, that being said, let's go see what that really sums up to. So a reflection, if we reflect the point A, it becomes A prime when we reflect over this line M, right? That original point A and the new point A prime is always going to be perpendicular to the line of reflection, and it's going to intersect by passing through the midpoint. So that's where we get the perpendicular bisector from. And if A lies on M, then its reflection is itself, aka like that fixed point before. If it's already on the line of reflection, it's staying still. Now, just like any other type of rigid motion, reflection being no different, it would preserve length and angle measure every time. Okay, so what properties will remain unchanged is your length and angle measure. Avoid ever saying size and shape. Remember, size and shape, not going to get us full credit on the Regents, so we don't want to ever even waste our time with it. Going on to exercise 4, we're actually going to try it on the Cartesian plane now. Remember, Cartesian plane is a fancy way of saying the coordinate grid versus what we were doing before. Since there was no grid involved, that was the Euclidean plane. So anything that talks about spatial region and we're just kind of working through out there, that is Euclidean. In here, once we have graphs involved and we're talking about space, now we're back to Cartesian. So we have the line segment AB given to us. We have the endpoints. We'd like to see what happens when we reflect in the y-axis, then follow it up by a rotation of 90 degrees counterclockwise about the origin. So first, let's just do this. I'm going to write out A, just so I have my points together. So that was 4, 7. And B was 8, 1. Now, the first type of transformation that's happening is a reflection in the y-axis. So that's what we're going to do to get A prime and B prime. So the easiest way I know for us to get that reflection in the y-axis is to just look at our graph. Okay, so here is my line of reflection right now, this y-axis, and we're going to use that to help us. So right here we have our line of reflection. And when we have that line of reflection, remember we said that it was going to be a perpendicular bisector. So that's one big thing that we want to make sure we're keeping in mind. So we're going to use that line to kind of help us. What I would do is just draw in the line that's perpendicular. Now, since I have I have a vertical line, I would want a horizontal line to come through. And it's a bisector, so this point right here on the line of reflection should be my midpoint. So from A to that midpoint is 4. So if I have 4 on one side, I want 4 on the other. And that's going to be my A prime. So A prime falls at the point -4, 7. Okay. We're going to do the same thing with B. So I have a vertical line. I know that this point right here, that's because I'm going to want the horizontal line towards it so I can make the perpendicular. Then I'm going to count over 8. And then I count over 8 in the other direction as well. So that's going to be -8, 2. And so that is our new line segment. So I'm just going to draw it in here with like different colors. So this here, that is our new line segment. Okay, and then if I folded my page over on the y-axis, then you would see it exactly the same. That's always the go-to check. So that's A prime and B prime. But we still have to follow it up with a rotation. So when we rotate, just as a follow-up reminder here, the rotation rule of 90 degrees, we saw it in the previous lesson and the first lesson, XY, that changes to -YX. So if I'm going to get the double prime here when I'm following that up, well, when I switch that, I'm going to have -7, -4, and I'm going to have -2, -8. So here's my A prime and -2, -8. All right, so there's our points. We've stated them and we've labeled them. Now, are A, B, and A double prime, B double prime the same length? Of course they are. Okay, now it doesn't ask me why, but we should know a reflection and a rotation are both examples of rigid motions, and rigid motions preserve length and angle measure. So when they ask if they're the same length, they definitely are. Okay, and that's what we're going to follow up with in C here. Reflection and rotation are both rigid motions. Now it does ask me what single transformation could map these two onto each other. So this one was just kind of like a follow-up kind of question, but I'm looking at the original AB and my A prime, B prime, or my A double prime, D double prime. Now I just noticed I didn't mark them with double prime, so I'm going to go in there and make sure they're there. That would be a silly mistake on my part, so make sure they have your double primes because we already had an A prime, B prime. Well, in this case, we saw this in the homework the other night in one direction, but we want it so that we can get A onto A double prime and B onto B double prime. I'm just going to get rid of that extra stuff for now. Well, if I look, there could be a reflection hiding in here. It's actually a reflection of the line y equals -x. Oh, that was a terrible drawing, so I'm going to try to fix that up. See if I can do a little bit better. Yeah, bear with me on that one. I'm a little off with my thing. It's not calibrating the same way. But that would be a reflection over y equals -x. And we'll look more at that. So you don't have to worry about too many of the specifics of things like that just yet. But that would be our reflection. One final idea for today. In the diagram below, we have the measure of angle BAC and the measure of DAC are equal. So remember, BAC is that angle in here, DAC is in here. Based on the properties of rigid motions only, answer the following questions. So angle BAC was reflected across AC, then why must AB fall on top of AD? Well, remember what the line of reflection does. Okay, so if angle BAC has that AC in there, and it was reflected across, well, if we know angle BAC is congruent to angle DAC, we know that we have two congruent angles there. So if you have two congruent angles, that means that AC bisected angle BAD. Okay. And if that's the case, if they're mapping onto each other, we know that those angle measures would have been preserved and angle BAC would be mapped onto DAC. Okay, so if the angle measure is preserved, we know that those two angles are good. Now, under that same reflection, would point B have to lie on point D? Well, let's just look at it. B is up here and D is up here. While it might not be drawn to scale, there's no indication that that definitely has to happen. Okay, we don't know. AD and AB were never indicated that they're the same length or anything similar to it. We know that the angles are going to be equal to each other, so that means they're going to be preserved, but we didn't know anything about the segments AB or AD. So we know that it's going to land, that point B would land somewhere along the line AD, like it could probably be somewhere maybe over here, but we have no idea if it would land on D, and it doesn't look like it would in this case. All right, guys. That should be it for now. Tomorrow in class, we're going to do some practice and see how we feel about the transformations we've talked about so far. All right, guys. Thank you for watching.